Welcome to Homework 12. We're going to be going over problems 3.2-6 and 3.37. A circular aluminum tube subjected to pure torsion by torques has an outer radius equal to 1.5 times the inner radius. If the maximum shear strain in the tube is measured as 400 E-6 radians, what is the shear strain, gamma 1, at the inner surface? So it's given us a relationship between two radii and a shear strain, and then wants the other shear strain. Conveniently, due to the relationship between strains and radii, we know that we can make this similarity approach. So basically, as you twist something, the further away you are from the center is where there's going to be more twisting. Or in other words, the further away from their center, as I have drawn here, you have greater strain, which is why I'm saying that using the geometry approach, y1 is to y2 as r1 is to r2. So I can set up a little ratio equation here. Since we already know the r2 is 1.5 times the inner radius r1, and we have those flopped, I can say that if I multiply my y2 to the other side, then it's going to be being divided by 1.5, and I can find my inner strain, shear strain, that is. If the maximum allowable rate of twist is 0.125 degrees per meter, and the maximum shear strain is to be kept at the value that it already is at, by adjusting the torque, what is the minimum required outer radius? So radius and shear strain are related by theta, which is our allowable rate of twist, and it's saying that our maximum strain is going to be our strain of our outer, so we're not changing anything there, so I can say my gamma sub m is the same thing as gamma sub 2. Then my radius has to be at least large enough to match that ratio. So that's what I have here. R2 is greater than or equal to y sub 2 over theta. And since we're finding the minimum, we're just going to set it to equal. However, our theta is in degrees per meter, and we need radians so that our units work out. So I'm just going to make a quick conversion, and then we can divide by theta and get our value of 83.2 millimeters. While removing a wheel to change a tire, a driver applies forces P equals 25 pounds at the ends of two of the arms of a lug wrench. A wrench is made of steel with shear modulus of elasticity G. Each arm of the wrench is 9 inches long and has a solid circular cross-section of diameter D. Determine the maximum shear stress in the arm that is turning the lug nut. So if we look at our little schematic here, we have some forces creating torques and our lug nut at A. So our shear equation, which is what we're looking for, is 16t over pi d cubed, and this is for circles specifically. We can solve for t because it gives us how much force he's pushing on the sides with, and then we already have d, and we can solve for it. Determine the angle of twist of the same arm. So because there's going to be some resistance by the lug nut, and we're also putting forces in the other direction, and it does have some elasticity, it will be twisting, and that's conceptually what they're asking for. So gamma, angle of twist, is TL over GI polar inertia. And our polar inertia for a circular shape is pi over 32 d to the 4th. So we have our t, which we solved for in part 1. G is given. We can solve for polar inertia as a function of our diameter, which is given, and we get our answer. So shear strain, rate of twist, and angle of twist are somewhat confusing, especially rate of twist and angle of twist, since those sound like the exact same thing. So we're going to go over those. So if we have some torsion, some torque on a thing, on some member, then we're going to have some shear on our member, with the greatest shear appearing on the furthest end, which is why we get that our shear is TR over our polar inertia. Now we're using our polar inertia because it is going in the axis of our tube, which is denoted, it's the in and out of our cross-sectional area. So if you have a cross-sectional area of our tube, it's the circle, X is horizontal, Y is vertical, and our polar is in and out of that plane. And then R, because the further away you go, and then of course T, the greater the magnitude of our torque, the greater shear we get. And that's how this equation is created. Then there's also a relationship with how rigid it is, because the less rigid it is, the more it's going to strain. And this can be compared with the normal strain relationship, where tau equals G gamma, sigma equals E epsilon, and it's the whole thing. E is elasticity, G is rigidity or shear elasticity, same thing. E is strain, gamma is shear strain, and so forth. So if we have our little circle here, further out you go, you have greater strains as compared to the side where it doesn't have to go as far to match where the rest of the body is being stretched. So that's why earlier we were able to say that gamma was proportional to R, and that proportionality is our theta, our rate of twist, which if we were to draw on our member here, then our rate of twist is kind of that angle, and our theta, sorry, I might have said that backwards. Phi is our angle of twist, which is accurately drawn here on this image, and theta, which is our proportionality constant, is our slope between gamma and R. So if we look in this triangle on the right side, the red triangle, on the right side of our cylindrical member, we have a rise of gamma and a run of R. And so that slope there, that rise over run, that is our theta, which is why it's very simply that gamma equals theta R. So one of them is going with the face, our theta is going with the face, and our gamma is going through and into the face along the side of the member. So as you can imagine, the longer our member is, the smaller gamma would be, the angle of twist. I hope this was helpful. Thank you for watching.